in this video we're going to talk about if you have a pressure that's being applied across a rigid body. So in this case we have a pressure that is applied across our rigid body, right? And we know that that pressure can be defined as a function of x and y. We want to be able to determine what would be the total force that would be due to that pressure, which we'll call that total force our resultant force due to that pressure. And we want to determine where would you apply that resultant force on our plate or on our rigid body. So in this case we have a square plate, and it is equal to it is applied, that resultant force is applied at x bar and it's applied at y bar relative to our coordinate system that we defined. So in order to determine our resultant force and our resultant and our locations of our force, we can use the following formulas. This is we can define our resultant force as being equal to our pressure distribution, which is a function of x and y, times our differential area. You can think of that also in terms of being the total volume underneath this curve here. So if you thought of this as being our volume, alright, the total volume underneath that curve would give us our resultant force. Alright, and then to determine our x tilde and our y tilde, or sorry, our x bar and our y bar, are locations of where these this resultant force would be applied, we just have to multiply our pressure distribution by x, and our pressure distribution by y for x tilt bar and y bar respectively. All right, so so that's it for distributed loads. It's very similar to what we did in Chapter 4. The only difference between these formulas and the ones that we found in Chapter 4 is that Chapter 4, those were 2D equations for distributed loads that look like W of x. In this case, these are 3D cases where we have pressure instead of distributed load as a function of x, y. Otherwise, it's exactly the same concept. The formulas are very similar. Alright, so that's the conclusion for distributed loads across a rigid body.